Welcome to the lecture series on linear models, or to be more precise, linear statistical models. When I taught this course the last time, I generally relied on my personal notes, which you can still see in my web page. But this time, because of the pandemic, I will prefer to stick to one standard textbook, and that textbook is this one, Linear Models with R by Faraway. It's a nice book. One of the greatest virtues of the book is that it does not reduce the topic of linear models to merely an application of linear algebra, as many others books do. It will illustrate the statistical aspect much better than other books, and also will give you some hands-on training. Now, most of the course will work with this book, but during the later half of this course, we shall be using another book also by the same author, which is called Extending the Linear Model with R. And then you will need this book. Only a few chapters from this book will be needed. Just notice that I will be using the second edition of these books. This is second edition, and if you look at the earlier one, that was also the second edition. So make sure you get the second edition so that when I refer to page numbers or chapters, etc., you know exactly where to find the things. Now, linear models is something which is like a workhorse in statistics. There is nothing very deep going on here. It is something like solving linear equations. In usual mathematics, this is not the profoundest possible theory, but it is very useful. It works as an inevitable intermediate step in some more ambitious computation. So, having a good grasp of linear model is very important in order to learn statistics. Now, just like any other statistical method, you really do not learn it unless you carry things out in practice. And for that, you will need some kind of a software, and the software that we will be using is R. So that is a free open source software, as you already know. So make sure you have this R installed. And the book by Faraway has various data sets, etc. And all these things are bundled in one package called Faraway, which you can install. So you can get all the data sets and some problems, etc., bundled inside that one package. Now we shall start our exposition with one example. This example, by the way, is not taken from the book by Faraway. And indeed, sometimes the examples that I will be using will be not from the book. We will be following the book more or less closely, but my exposition will not be verbatim copy of the book. So in this example, we will be starting with a problem which is faced by many scientists. Suppose I have a number of molecules. So here I have one molecule, here I have another molecule, and here I have another molecule. I say that these molecules consist of two types of atoms. I have the red atoms and I have the blue atoms. Now I want to measure the masses of these two types of atoms. So what can I do? I can take the atoms separately and weigh them. That is pretty difficult, but they are only available as compounds, so I can measure a molecule of a compound. Then I can try to solve a system of linear equation. So in this case, I suppose measure the weights or the masses of all these molecules, and I get, so I have to do some kind of an experiment to do that. And as a result, I get some numbers. Suppose the numbers turn out to be like this. So I measured one molecule of this type, I got 9.8, whatever unit. For these, I got 9.1, and for these, I got 7.0. From this, I want to find out what are the masses of the two types of atoms. Now that should not be very difficult, so let's see the first molecule. Here how many do I have? I have red 1, 2 and 3, so there are 3 red things. Suppose each of them has got mass A, and how many blue type? 4, so 4 of type blue. So if I just try to make an equation out of it, I will get the equation 3a plus 4b equals that measured 9.8. Similarly, for this one, I have how many red? 4 red and 1 blue, that is 4a plus b. I do have 4a plus b, that is equal to the 9.1, and in this case I will have 2a plus 3b, 2 red and 3 blue. So I have got these things. So I have got 3 equations in 2 unknowns. Now we know that if I really want to solve it, it's enough to take any 2. So but I have these 3 measurements. So you might be tempted to try to solve all these 3 equations to get a and b, that is, try to get values of a and b which will satisfy all the 3 equations. If you give it a try, then you will find that this system of equation happens to be inconsistent. You cannot find values for a and b, no real values of a and b for which all these 3 things will hold simultaneously. But how is that possible? The reason is all these things are actually approximate. These numbers, this 9.8 or this 9.1 or this 7.0, these are all approximate quantities. They are result of measurements. So ideally what I should have said is that these are approximate. I have changed my equalities to approximate equalities. Now the point is, well, approximate or not approximate, how do I really solve this? I just now notice that if I ignore the approximation and treat them as exact equality, then I just cannot solve it. But that is how life is. You never get measurements which are exact. Then what do I do? Well, you might be tempted to say that, well, ignore any one of them. Just solve the other two. Suppose I take the first one and the second one and solve them, treat them as exact. True, but remember that there is some amount of error involved here, So the values that you get will be not exact. However, this equation, this third approximate equation, also gave you some information. Now, why did you throw this thing out and keep these? I could have thrown this one out and kept these two. I could have thrown this one and that one. I could have just thrown away this one and kept this one and that one. In each case, you will get different answer. Which one should you choose? All these things actually give you information. Throwing away any of them is not a good idea, and even if you decide to throw away, how do you choose which one to throw away? So, throwing away is not good. What we want to do is, we want to take all these things into account. I hope you understand that even in this artificial example, we have given you a situation that is faced by all working scientists. You have some theory. The theory predicts that you should see this, then you measure it, and the measurements are all some amount of a little bit of random, there is some random measurement error. So the equation that you will get will always be or almost always be inconsistent. There must be some way by which you are able to solve an inconsistent system of equations. And that is exactly what linear models do. It's the way of solving inconsistent system of equation, or something that we should more precisely call approximately consistent system of equation. And this will take us to some fascinating application of linear algebra. So here is the equations that we had. We have 4a plus 3a plus 4b approximately equal to 9.8, 4a plus b approximately equal to 9.1, and 2a plus 3b approximately equal to 7.0. All these things are approximate. Now let us try to recast this in a way so that we can use linear algebra efficiently. I will just write it in the following way. I have just written, instead of writing 3a plus 4b, I have taken all the coefficients of a as a column vector multiply that with A. Similarly, all the coefficients of B as another column vector, multiply that with B, and the other side, all those measurements as another vector. So I have this system of equations. Just convince yourself that this is exactly the same as whatever I had shown earlier. But when I put it in this way, you can see that trying to solve this system of linear equations basically means trying to express this vector as a linear combination of these two vectors. Now, when I say it's approximate, when I say it is inconsistent, I basically mean that this vector may not be in a form that can be represented as a linear combination of these two columns. In other words, this vector may not be, I said approximate, so by chance it could be, but typically it will not be something that belongs to the span of these two vectors. So if I consider these two vectors in R3, then it does not belong to the span of these two vectors. These are in R3. Let's look at it in the form of a picture. This picture that you are seeing is possibly the most important picture that you will have to remember all throughout this course. So here is our system. Now, let's understand this picture carefully. I have got these two vectors. I have shown them as these red vectors. This is in R3, so I am just showing them as just two arrows. And that's the origin. This point is the origin. This cyan dot is the origin. There are two arrows that are coming out. One of them is this 342 and the other one of them is 413. This is just a fictitious picture. I am not very careful with all the numbers, just showing it. Now the measurement vector, this 9.8, 9.1, 7.0, that is this green arrow. Now all the vectors that can be represented exactly as a linear combination of these two, namely the span of those two vectors, that red vectors, that is this pinkish plane. You see, in this case the green vector is not lying on this space. That's why we say that it is inconsistent. Now, what do I mean by saying that I want to solve this inconsistent system? Well, the natural thing is, if you cannot find A and B such that this will be exactly true, at least try to make it as close as possible. In other words, try to find that point on the plane. Remember, every vector in this plane is of the form some A times 342 plus some B times this 413. So try to find that vector which is the closest possible to that. Now you know how to find that, right? What I will do is I will take a light and shine it perpendicularly on this plane. That's what I have done. I have not shown you the light, but when I am shining that light perpendicularly down, it will cast a shadow. And that is the shadow that you are seeing. This kind of purplish arrow is not an arrow really, it is the shadow of this green arrow when the light is shining perpendicularly on this plane. So if this is the direction of the light, then this angle is 90 degrees. So this is perpendicular to the plane. It is perpendicular to every vector on the plane. Then this will be the point closest to that point. That we all know, right? So drop a perpendicular to get the closest point. So what we will do most of the time is to choose A and B such that this side happens to be the point closest to that point. That point on the plane which is closest to our desired point. This I am sure you have recognized as the so-called least squares technique, because when I say distance, I mean the Euclidean distance, so that is sum of squares, square root of that. So you are basically minimizing the Euclidean norm of this vector, and that's why it gives you the orthogonal projection. So it is nothing but the least squares technique. And this is the most important thing that you have to remember in this course. I have not yet through the course for half an hour, you have already learned the most important thing. Now, so how do I do it in general? That's pretty simple. So I will just show this in general. So here I had two vectors and I wanted to write it as a linear combination. I wanted to express this as a linear combination of those things. In general, we will be working with a system like this. So I will have x and I will have beta, and y will be approximately equal to that. So I have got y and beta. These are vectors. And typically the sizes I will take n cross 1, and this will be n cross p, this will be p cross 1. So in my example, n is equal to 3, so there are 3 things, and p is equal to 2, there are 2 such vectors, and my beta, that is ab. So in my example, I have x given by this thing. What are the things? 3, 4, 2. 3, 4, 2, and I have got 4, 1, 3. 4, 1, 3. So 3, 4, 2 and 4, 1, 3. So these are the vectors that I will be. So this is the matrix that I will be working with. Now instead of writing it like this with an approximate thing, most of the time we prefer to write it as this plus an error. We write it as vector epsilon, that is also n by 1. And this is the general form of a linear model. That's what we call a linear model. A linear model is just an approximate system of linear equation. Of course, later we are going to put certain assumptions on this epsilon, some statistical assumption. After all, it is linear statistical model, not just linear model. So we are going to put some statistical assumption, but more on that later. For the time being, how do we really find out the thing that I mentioned, namely that orthogonal projection? I just use the term orthogonal projection. By this I mean when you shine light perpendicularly on the screen, then wherever the shadow is, that is called the orthogonal projection. How you find that point? How do you find this particular vector? It turns out there is a nice way of doing that. Possibly you have already seen that in your linear algebra course. If not, don't worry about it. I will just tell you the technique. The technique goes like this. You will start with, let me just see. So you have this system, x, beta, approximately equal to y. Now what I will do is, I will just pre-multiply both the sides with x transpose, pretend that this is exact equality. Mysteriously, if you solve this system, the beta that you will get will give you the required solution. So this is called the normal system of equation, or normal equation. Now how do we get that is something we'll get into that later. It's a little bit of linear algebra. I do not want to get into that on the very first class. Now you might ask, what happens if this itself turns out to be inconsistent? Fortunately for us, this will be always consistent. Always consistent. Irrespective of what y you choose and what x you choose, this system is bound to be consistent. And if it so happens that this is non-singular, by the way, it's also a square system. You can see that this is a square system. It is p cross p, p cross 1, and this is p cross 1. So it's as many equations, as many unknowns. If this also happens to be non-singular, you are very happy. You will get beta equal to x transpose x inverse x y. And this is, of course, obtained from the data. This is part of the measurement, so we'll generally call it beta hat, in which case the solution is also unique. However, if this is not non-singular, then the system, I said it is always consistent, but may not have unique solution. We'll get into all those cases later. The simplest possible case is when it is non-singular, you can just find the unique estimator, and that is what is called the least squares estimator. Least squares estimator. Well, that is basically all that I wanted to talk about in today's class. Now, you must remember that whatever I am saying is something like a supplement to what is given in the textbook. For example, the textbook will tell you some statistical aspects of it. For example, when you get data, you must first make sure that you have made the initial plots and things like that, instead of diving directly into some mathematics. You should first make plots and see how close the thing is to being consistent, whether it is at all a meaningful problem, if there is any imperfection in your data and all those things. Now the book gives you some hands-on practice session for those things in the very first chapter. So whatever you have done basically is a supplement of the first chapter of the book. So you should read the first chapter of the book, the introductory chapter, a short one, and also read up to what is called the Gauss-Markov model in the second chapter. Okay? So we will take up the details later in our next class.